for solution procedure. Okay, where delta T is positive. Okay, so I'm going to, so what we have is we have a rod. Okay, so again we have support on both sides. Okay, then we remove, so this is point A, this is point B. We remove, so step 1, we are going to remove support at point B. You can also remove support at point A. Yeah, the answer will be the same. My bad. I'm going to do it on the next page. Okay. Because I need space. Okay. Then we remove the support at point A. Sorry, point B. So when that's the case, our structure can expand. Okay. So this is our point A. Right. We remove the support at B. So now we can calculate, this is exaggerated. We can calculate from here, we can calculate delta T. Okay, so we can determine delta T, and delta T can be determined by alpha multiplied by change in length multiplied by original length. Then step 2, okay, we are going to include a redundant load at point B, right? So we're going to push it back. Okay, so we're going to push it back. Right. So our original, I'm going to use, right? Our original is here to here, right? So this distance from here to here is our L0. Okay. So the second step, we're going to push it back. Right. So we allowed it to grow. Okay. Then we are going to from here, we're going to push it back with a redundant load that we're going to have, R. Okay. So the pushing it back is what we call delta R. Okay. So this distance from here to here is our delta R. And delta R is equal to minus R L0 divided by AE, because it's mechanical, right? It's a force. Okay. Then from here, you just need to do delta T plus by delta R will be equal to 0. Okay. Then you can calculate your stresses. Now I will do the opposite. Okay. So what if now delta T is negative. Okay, so it's still the same. The original is still the same. I'm going to copy the original. Okay. So this is the original. So when the change in length or the change in temperature is reduced, right? We know that we are going to induce a contraction. The length will be shortened. So now the length has been shortened by this much. Okay. And this length has been shortened from here. We will go down to here, and this is due to temperature. Okay, so this is our point A. So when we remove the support again, so when it's the case, the change, the deflection due to temperature is equal to alpha, okay, delta T L naught. And now we know that this will be equal to what? For this case, it's going to be what? Negative. Right? For the other cases, increase in temperature will be positive. So from here, again, we have to push it back to 0 deflection. Okay, I'm going to change the direction of the arrow. Okay, we have to push it back. Right? So we have to pull it back to R in this direction. Why we have put it back? Because now our starting point, right, is a smaller length. Okay, so now we have to push it back to delta R. All right, so delta R over here, right, delta R will be equal to R positive because it's in tension divided by AE. Then again, delta T plus by delta R will be equal to 0. Okay. Right. So let's look at our last example, and this example can be deemed confusing. Okay. So I'm going to do the last example for the day, and bear with me. Okay. It's one of the most confusing question, but it's not impossible to understand. Let me copy and paste first. So this is example number 2. And then I'm going to copy the image. Hey, I think I did something silly. Okay, this is the question. So this is a very well-known question, but it's pretty abstract. Okay, why I picked this question? Because there's a gap. Gap. Okay, before let's read the question. I'm getting ahead of myself. Okay. So at room temperature, okay, there's a gap of 0.5. So we know from here our T0 is equal to 20 degrees C. Okay, between the. So what this means is when there is a gap, right? The members A and B are allowed to move freely, right? So when that's the case, right, stresses at A and stresses at B will be equal to 0. when there's a gap. Okay. So at 0, the structure is allowed, the total expansion of the structure of member A and B will be equal to 0 whenever there's a gap. Okay. Then at a later time, the temperature has reached 140 degrees. So T1 is equal to 140 degrees C. Okay. So it asks us to determine the normal stresses in the aluminum rod and the change in length. Okay. So it's the gap that is throwing us off. Okay. So let me elaborate what is going on down here. Okay, in terms of graph. Okay. So now I'm going to draw a graph. Right. So this is gap. And this is, it can be stress on the aluminum or stress of the stainless steel. Okay. So this one is stress of aluminum or the stress of stainless steel. Okay, stress. Okay. So over here is 0 gap. Okay. So this is 0.1, 0.2, 0.3, 0.4, and then you have 0.5. Okay. So when there's a gap, right, there is no what? There is no stresses. Okay. So we started, I'm going to draw, we started at 0.5, right? So it's still maintained at 0 on the stresses. And then when the gap is 0.4, still no stresses. 0.3, okay, no stresses still, okay, because there's still a gap. 0.2, no stresses. 0.1, no stresses. And then when we hit 0, right, exactly 0, no stress. Okay. Now, when the gap gets to be equal to minus 0.1, minus 0.2, minus 0.1, 0.2 means it's overlapping now. Okay, now the gap is 0. So what will happen is I'm going to draw, okay, this is just a trend. I'm not saying this is just a trend. Then the stresses will start to increase. Okay. The stresses will start to increase. Okay. And this one will be stresses for point. Okay. Stresses for the steel. And then the next one is the stresses of the aluminum. Now, this is just the trend. Okay. On the left hand side, when the gaps get more negative, the stresses what? Increase. Okay. Now, physically, you cannot get negative stress. I mean, sorry, negative gap. But negative gap means it's in full what? Contact. But what I want you to see is this. Whenever the gap is positive, okay, no what?
Stress.
Okay, no stresses. Because you allow what? Motion. Like, that's why I elaborate down here, right? I elaborate down here when I was explaining, right? There is no stresses associated with temperature change when there's no restriction in what? Motion. A gap means there's no restriction in motion. 0 gap, then you restrict the what? The motion. Okay, right. So let's calculate the deflection now. Okay.